Back to Miss Sogram's Maths. This worked solution video is for the practice externals available from D&D Resources, so a big thank you to them for allowing me to use their resources and make these videos for you. The link to their materials is in the video description if you would like to go and order a physical copy, which I would highly recommend if you're doing practices for the externals, is to actually work through these on paper. So this is practice external assessment number 4 from the complex numbers booklet for standard 91577. Now let's get it stuck into question 1. These are achieved questions to start the paper off, so you can do them entirely on your calculator. So that's what I'm going to do here. I'm using the complex options that we have available to us, so I can put this straight into the calculator. So first of all, we have I times by 2 minus 3i is replacing the z there. Take away the conjugate of z, which is 2 plus 3i, like so, and enter that. We've got an issue. I did the wrong kind of subtraction there. There we go. So this gets us the answer of 6. I'll write the whole thing in of what we did there. Minus 2 plus 3i equals 6. For part B, we want there to be no real solutions to this equation, which means we'll be considering what happens to the discriminant of this equation. But before we do that, let's multiply through by the k so that we're not needing to worry about fractions and what's happening there. So everything multiplied through by k looks like this. So then the discriminant, b squared minus 4ac, is, well, the b is k, because it's this bit to do with the x. So that's k squared minus 4 times a, which is 1, times c, which is 4k. We need that to be less than 0. So this is k squared minus 16k is less than 0. Now we can factorize k squared minus 16k to be k brackets k minus 16, and we need that to be less than 0. Now, considering when this quadratic dips below 0, we can get the roots from this would be 0, this would be, or if we were thinking if it being equal to 0, that would be k equals 0 and k equals 16. So it drops below 0 here at 0 and 16, so it's everything that's in between there. So k must be between 0 and 16. Okay, modulus means we are doing the square root of the real part plus the imaginary coefficient, and that will be equal to 5. So a squared plus p squared equals 25. On the other side of things, we've got the square root of 2a squared plus 5p squared, and that equals 17. So then we'll have 4a squared plus 25p squared is equal to 17 squared, which is 289. Now we'll solve those simultaneously. Let's say that p squared equals 25 minus a squared. And then sub that into this one. So 4a squared plus 25 times 25 minus a squared. So taking out the p squared and replacing it with this piece. So we end up with, we've got 4a squared minus 25a squared. So 4 minus 25 is minus 21a squared. Plus 25 times 25 is 625 is equal to 289. So minus 21a squared will be 289 minus 625. So a squared, if we divide by the negative 21, is 16. So a would be plus or minus 4. So if a is plus or minus 4, we have a squared plus p squared equals 25. So that makes 16 plus p squared is 25. p squared equals 9 in that case. So then we have p equals plus or minus 3. Okay, now for part D, let's start by putting this all over a common denominator. And then we want to be able to find the values of p so that what we end up with is entirely real. So the imaginary part will be equal to 0. That's what I'm aiming for. So if we put this over a common denominator of p minus 2i, p plus 2i, we have 1 plus I on the left needs to be times by the p plus 2i, minus the pi on the right has to be times by the p minus 2i. Okay, now on the bottom we've got a difference of squares there, so it's p squared minus 4i squared. And on the top we're going to have p plus 2i plus ip plus 2i squared minus p squared I plus 2pi squared. Okay, now let's sort through the I squareds in there. So we've got p plus 2i plus ip minus 2, because that I squared becomes a minus 1, minus p squared I, and again this I squared becomes a minus 1, so it's minus 2p over p squared plus 4, because this I squared becomes a minus 1. Now collecting up the real and imaginary parts, the real parts we've got p minus 2p, so we have a minus p, we've got a minus 2 all over p squared plus 4. Then the imaginary parts we have are the 2i, the ip, and the minus p squared I, again over p squared plus 4. Now I can take out the I that's in each of these bits on the top here and just have it as being on the outside here. Now if this is purely real, it means that this imaginary bit here will be equal to 0. So that's where we're going to with this next. So 2 plus p minus p squared over p squared plus 4 must be 0, which gives me that 2 plus p minus p squared is 0. And for that one, just to finish it off, we can do equation solver. We've got a polynomial with degree 2. The coefficient of what's x squared in the calculator, but p squared here is minus 1. Then the x term is the singular p term here, there's one of those, and the constant is the 2 just here. And we will solve that. We've got p equals 2 or minus 1. Part E, we've got u and v, but within the v we have this m that we don't know. We need to work out what m needs to be so that the argument of u times v makes pi by 3. So let's first of all write down what uv would be. So this would be 2 plus I times 1 minus mi. So if we expand that, we will have 2 plus I minus 2mi minus mi squared. So the I squared here becomes a minus 1, so that'd be a plus m on the real part, and the imaginary part is going to be 1 minus 2mi. Now to use this bit of information, that the argument is going to be pi by 3. So if we think about what that means on our argand diagram, we've got an angle here of pi by 3, or 60 degrees. And it makes this triangle here, which is one of your special types of triangles. Now, if this length here was of 1 unit across in the real direction, then we would have a hypotenuse of 2 and a height of √3. So we have the ratio between the real and imaginary parts as being 1 to √3. So if we write that down, so real to imaginary is equal to, the real part would be 1 to √3. And just in case you didn't quite follow that, those special triangles are available to you on the formula sheet, and you should recognize that pi by 3 is one of the particular angles that are interesting to us. There's pi by 3, pi by 6, pi by 4, all of those ones that give us some particular relationships relating to those special triangles. So look that up on the formula sheet. Now, if the real part of this was 2 plus m, then the imaginary part would be, this is like saying 1 times 2 plus m. The imaginary part would be √3 times, what is it, 1 minus 2m here. So this bit here. Another way to think about it is saying the imaginary part is √3 times bigger than the real, which means that our real part being 2 plus m will be √3 times, or sorry, if we do that times √3, that will be equal to our imaginary part of 1 minus 2m. So now let's work on solving that. And it's going to involve surds, so I can't just put it into equation solver on this particular type of calculator that I have here. Although if you have the newer model, you could do this all in surds and put it in equation solver. I'm going to need to write this out fully, so we'll have 2 √3 plus m √3 is equal to 1 minus 2m. Let's bring the m all over to one side, so we'll have 2m plus m √3. And the numbers on the right hand side, so 1 minus 2 √3. All I've done is take the 2 √3 over and the minus 2m over here. So if we take out a factor of m, we've got 2 plus √3, and that is equal to 1 minus 2 √3. So m is 1 minus 2 √3 over 2 plus √3. Now, this question doesn't say to give it in any particular form, but just for completeness, I'm going to rationalize the denominator because you might be asked to put it in a particular surd form. So we'll times it by 2 minus √3. And we have 1 times 2 is 2. Then we've got minus 4 √3 minus √3 plus 2 times √3 times √3 ends up being 2 times 3, so that is a 6. All over 4 minus 3. So 4 minus 3 is the 1. 2 plus the 6 is 8. Minus 4 minus another √3 is going to be minus 5 √3. On to question 2. Now, for this one, there's a long way and a short way. The long way is to say if I've got those two roots, then x minus one of the roots is a factor. So I'll just write that down. X minus the other root is also a factor, and then you can expand that. However, we can actually do this a little faster if we know the rules of sums and products. Okay, so the sum of roots, if we pop that into our calculator, we've got 4 √2 there's the I, and we're going to add on 5 minus √2 I. That gets us to 10. The product is to times those two things together. So let's just go back here we'll pop some brackets in there. And just to save some time, I just skipped ahead a little bit. So multiplying those things together gives us a 27. Just be careful with inputting your square root next to the I. That actually did need brackets around the square root too for that to come out properly. Now, when it comes to a quadratic, the sum of the roots is equal to minus b over a in our quadratic formula, and the product is equal to c over a. So if we set a to be 1, then we can have, remembering this is ax squared plus bx plus c equals 0. So then if we set a as 1, we can have x squared minus 10, because this has to be equal there. And then the c portion will be the 27. And you can check on your calculator, pop that in and solve it under equation solver, and it will give you the right answer. Now, the answer in the back of the book for this one used a z here. Since it wasn't specified in the equation, in the question, whether we're doing z's or x's, it doesn't really matter. This equation here would also have those roots there. Okay, on with b. Well, we've got two things being multiplied by each other, like this, and it's equal to 9 plus 20i. Now, since we've got k in both portions there, we are going to need to do the expansion rather than just doing a backwards working through division for this one. So if we expand these two brackets, we end up with 4k plus 2i plus 2k squared I plus ki squared is equal to 9 plus 20i. So let's take the real parts of this. On the left hand side of this, we've got here, because the I squared becomes a minus 1. So we'll have 4k take away k, so 3k is equal to 9. Therefore, k is equal to 3. And we'll just double check it with the imaginary portions. So the imaginary, on the left, we have 2 and 2k squared. So 2 plus 2k squared is equal to, on the right, we've got 20. Now, if k squared is 3, then we're going to go 2 plus 2 times 3 squared. Now, is that equal to 90? Well, we've got 9 times 2, and then add 2 makes 20. So k, we've confirmed, is 3. Not absolutely necessary to do that check of getting it both ways around, but it does help you in an exam to be able to know that it's working out. Okay, for part C, we're looking at this quadratic of x squared minus 4, and it's a factor of this cubic, and if that's true, we need to find the values of a and b. Now, there's a couple of different ways we can approach this question. I'm going to think about it as being x squared minus 4 gets multiplied by another ax plus b factor, where we don't know. Actually, I won't call those a's and b's because we've already got them in the question. Let's call this a c and a d. We don't know what the c and the d are, but we do know that if we multiplied them out, it's got to make 3x cubed plus ax squared plus bx minus 8. Now, let's have a look at how we can make, well, that's not a good color, hold on. How we can make the 3x cubed on the right. It has to come from doing the x squared times the cx. So therefore the c has to be 3 so that we can make the x cubed. So just looking at the x cubed, c must be 3. Now looking at the constants, so I'm going to put that x to the 0, the constant terms, well, we need to make minus 8, and that has to happen by doing the constants multiplied together here. So minus 4d equals minus 8, so d must be 2. So we have the other factor is 3x plus 2. Now we can expand out. We'll have x squared minus 4 times 3x plus 2. To make the x squared terms, you could either expand this whole thing out and then pick out what's a and b, or we can just pick out the stuff to make x squareds. So x squareds are made from doing x squared plus 2, so that would be 2x squared, And actually that's it because of the nature of how this is set up. So we can get 2x squared out of that. So therefore a is equal to 2. Now if we look at the x terms, to make x terms here, the only way to do it is to do 4 times the minus 4 times 3x. So we would have minus 12x. Therefore the b is 12 because that's what's going to go into this bit just here. If that expansion was multiplied through, we would end up with 3x cubed plus 2x squared plus 12x minus 8. For part D, we've got what looks like a reasonably lengthy bit of algebra to get on with. So let's start by subbing in root 2 plus I for z. And we're going to add on 1 over the conjugate, which is root 2 minus I. And then it will be multiplied, squared. Now we could attack this all in one, but I think that opens itself up to creating mistakes. So let's start by doing root 2 minus I on that bottom. Let's rationalize the denominator. Oops, not a times, we want a plus there. Root 2 plus I is going to be root 2 plus I on the top, and then 2 minus I squared on the bottom. Well, I squared is minus 1, so that becomes 2 plus 1. And we end up with it being root 2 plus I over 3. Okay, next let's add on root 2 plus I to what we just worked out was this piece here. So from over here, I'm going to add that on. Root 2 plus I over, gosh, here we go, over 3. So I want to put this over a denominator of 3 so that I can add those two things up. So now they're on a common denominator, I can put it all over 3. We've got 3 root 2 plus 3i plus root 2 plus I. So collecting up the root 2's, we've got 4 root 2. Collecting up the i's, we have 4i, and it's all over 3. Okay, now if we square it, we've got 4 root 2 plus 4i over 3 squared. So the top will look like this, and I'm deliberately writing it out twice so we don't miss any pieces. 3 squared on the bottom is 9. Now let's expand that bracket. We get 16 times root 2 times root 2 is 2, so that'll be times by 2. I'm just going to straight away turn that into a 32. Then we've got 4i times 4 root 2, which is 16 root 2i, but we also get that here as well, so there's 2 of them. We'll have 32 root 2i. Then we have 4 times 4i, so that will be 16i squared, which becomes minus 16, since I squared is minus 1. So 32 take away 16 is then 16 all over 9. Okay, for E, let's start by putting this left-hand side all over a common denominator. So that's got to go under over root x plus root k times root x minus root k. It will be equal to root k. Now let's see what happens to the top. So on the left, we've got to do root xk multiplied by the subtraction one that's on the bottom. And then minus this one here needs to be multiplied by this one here, just by putting it over that common denominator. So if we expand that top line, then root xk times x just here. Well, root x times root x will be x, so this will be x root k minus root x times k, outside of the root now because the square root of k times the square root of k becomes just k. Similarly with the next bit, we've got minus x root k and then minus root x k. On the bottom, we've got a difference of squares here, so we've got x minus k. Now this x root k cancels with this minus x root k, and we end up with minus 2 root x k is equal to, and at the same time I'm also going to bring this x minus k that's on the bottom up and multiply it by the root k on the other side. Now, since what I'm attempting to do is get x equals something, I want to sort this out so I don't have a square root x there. So I can do that by squaring both sides. So if we square this side and square this side, then on the left we end up with 4xk squared is equal to, and on the right we've got k, this will be x minus k squared. So x minus k squared will be x squared minus 2kx plus k squared. Multiply that through, we've got kx squared minus 2k squared x plus k cubed. And then if we take this bit over to the right, we can turn it into something that's going to look more like a quadratic we're used to seeing. So if we've got kx squared minus 2k squared x minus 4k squared x from this bit moving over, plus k cubed, that's going to be equal to 0. Okay, now minus 2k x squared minus 4k x squared, that becomes minus 6k squared x. We can also divide everything through by k. We're told that k is not equal to 0, so we can just divide that through straight away. X squared minus 6kx plus k squared equals 0. Now x will be equal to, using the quadratic formula, minus b, which is 6k, plus or minus the square root of b squared, so that will be 36k squared, minus 4 times a times c, so that's 4k squared. So this now becomes, and that's all over 2. Now let's tidy up what that looks like. We will end up with 6k over 2 is 3k, plus or minus the square root of, 36 minus 4 is 32k squared, or that will be root 32k over 2. Now we just need to check how we've got the solution here is we want to sort out that surd as well. So the 32 over 2, that's the same as saying the root of 32 over 4, that's root 8, which is 2 root 2. Now we want to take the k out as a factor, so this will be 3 plus or minus 2 root 2 times k. Okay, so let's start with trying to rationalize the denominator of each of those fractions that we are adding together there. That'll make the addition a little easier. So if we do root 3 over 3 plus root 5 times by 3 minus root 5 over 3 minus root 5, just tidy that up just a little, here we go. We will have 3 root 3 minus root 15 all over, well, the 3 times 3 is 9. We'll have a plus 3 root 5 and a minus 3 root 5, so they cancel out, and we end up with a minus root 5 times root 5, so that's minus 5. So this is 3 root 3 minus root 15 over 4. Then the other bit was root 3 over root 5 plus 1. We'll times that by, we need to make the square root part the opposite, so it'll be a minus root 5 plus 1. So we end up with a minus root 15 plus root 3 on the top. On the bottom, we've got root 5 times minus root 5 gives us a minus 5 plus 1. So we end up with this being negative root 15 plus root 3 over negative 4. I want to match up the denominator on these two so I can add them together. So let's just multiply everything by through by minus 1. We will have a 15 minus root 3 and a 4 there, and that's equivalent. Okay, so now adding them together, we will have 3 root 3 minus root 15 over 4 plus 15 minus root 3 over 4. Just realized we missed some square roots here. That was my mistake in the transcription over here. Whoops. So this will be the square root of 15 just there, and fix up this one. That's square root of 15. Okay. Now let's add that together. We have 3 root 3 take away a root 3 here, so we end up with 2 root 3. Negative root 15 plus root 15 here, so they will cancel each other out, and that will be all over 4. 2 over 4 cancels to be just a half, so we end up with root 3 over 2. So this one we're doing p minus 2 times the conjugate of q. Well, p is minus 3 minus 2i. And we are taking away 2 times the conjugate of q. Well, q is 1 minus I, so this is 1 plus I if we're doing the conjugate. And we'll go over and pop it into the calculator. We need to get our complex options there. Take away 2 times 1 plus I. And I have done the wrong kind of minus just there. There we go. So that's equal to minus 5 minus 4i. And finally, don't forget the last bit, which is to plot it on the Argand diagram. That's so easily missed when you're doing these questions. So minus 5 minus 4i will be just here. So that's p minus 2 conjugate of q. With loci questions, your first thing to go to is usually to express that z is equal to x plus iy, and then substitute it into the stuff you've been given, which in this case is this bit here. Okay, so if we're to write z into there, we will have the modulus of x plus iy minus a minus bi is equal to the modulus of x plus iy plus a plus bi. Now modulus means we do the square root of the real part squared, so that's x minus a, those are the real bits, and the imaginary coefficient, so that's y minus b all squared, is equal to the square root of, on the right hand side the real part is x plus a, and the imaginary coefficients are y and b. Okay, so then we would know that you can take the square root off of both sides, and at the same time I will expand those brackets. So we'll have x squared minus 2ax plus a squared plus y squared minus 2by plus b squared. I'm just going to move this over because I like my equals to line up. Here we go. On the right hand side, if we expand that, we have x squared minus 2ax plus a squared plus y squared plus 2by plus b squared. So I just have one little thing to fix just here. That was supposed to be a plus. I got carried away doing things a bit too quick. Okay, so now let's cancel all the things that are the same on the left and the right. So that x squared cancels with that x squared there. We have an a squared and an a squared. We've got a y squared with a y squared and b squared and b squared. So we end up with minus 2ax minus 2by is equal to 2ax plus 2by. Now we want to find the gradient. So our next step is, let's see if we can, now we want to find the gradient of this equation. So let's rearrange this to try and make it y equals something, and we'll be able to pick out the gradient quite easily then. So let's bring the y's over to the left. We'll have minus 4by is equal to 4ax. So then y is equal to 4ax divided by minus 4b. The 4's obviously cancel. We end up with that being a minus a over bx, and there's no plus, so you know how we have y equals mx plus c. The c is a 0 here. We don't really need it, but I'm just helping you to recognize this is the equation of a straight line, and so the gradient is that coefficient of x, so that's minus a over b. Part D, we're going to use de Moivre's to find roots, but before we can do that, we need it to be in the form z cubed equals something. So if we take the minus 8 over to the other side of the equation and bring up the k that will be multiplied there, so z cubed equals minus 8k. Now on an Argand diagram, we have no imaginary part here, so we're going to be on the x-axis at minus 8k over here. So in polar form, this will have a length of 8k and an angle going around here of pi. So that's where we're starting from. Now, for our first solution, we will be doing the cubed root of 8k, and then the argument gets divided by 3. So the cubed root of 8 is 2, so this is 2 k to the third, or cubed root of k, however you want to write that, cis pi by 3. Now, once we have our first solution, the other solutions are have rotational symmetry around the origin. So we've got our first solution at pi by 3 here. Our next solution will be, we have 3 solutions that are around that circle. So a full circle is 2 pi. If you divide it by 3, you'll have 2/3 of pi. So we're going to add on 2/3 of pi for the second solution. So z2 will be 2 times the cubed root of k, cis, and then pi by 3, add on 2/3 of pi by 3. Well, that just gives you pi. And the third solution will be to take this and add on another 2/3 of pi. So we've got the same length, 2 times the cubed root of k, cis of pi plus 2/3 of pi. So there'll be 1 plus 2/3, which is going to give us 5 pi by 3. But once we go all the way over and past that pi line that's just here, we prefer to reverse it and call it a negative. So we would come at it from this direction instead. So from the full circle, take off what we've got there of 5 over 3. So a full circle is 2 pi. If we take off 5/3 of pi, we'll get that missing piece. So we're going to do it as 2 times the cubed root of k, cis of, and because we're going underneath it now this way round, then it will be a minus pi by 3. Okay, last question for this practice paper now. So from this bit here, what we need to identify is just how much this bit is worth, and then we'll be able to find the modulus of it. So that's what we're aiming for. So 1 over x plus iy. If we take this piece over to the other side of the equals, we'll have 1 minus 3i over 2 plus I, and then take away 2 over 3 minus I, and we'll use the calculator to help us out there. So we've got 1 take away 3i divided by 2 plus I, and then we're going to subtract 2 divided by 3 minus I. Okay, we've got fractions there. There we go. So we end up with that being minus 4/5 minus 8/5 I. Now that was for 1 over x plus iy. So x plus iy will be 1 over minus 4/5 minus 8 over 5i. So let's do 1 divided by that answer. There we go. And we've got minus 1/4 plus 1/2 I. So the modulus of z will be equal to the modulus of minus 1/4 plus 1/2 of I. There we go. So we're doing the square root of minus 1/4 squared plus 1/2 squared. So 1/4 squared is 1/16. 1/2 squared is 1/4. So 1/16 plus 1/4 is 5 over 16. The 16 we can take out and square root it, so this is root 5 over 4. Thank you again to D&D Resources for allowing me to use this and make these worked solution videos for you. Hope you liked that and found it useful. Go look up the other videos that I have for the rest of their resources. Thank you.